All right, class, it's going to be your 7.4 lecture. 7.4 is kind of putting together what we've been doing. So we've had systems of first order differential equations. We can write them in vector matrix form by creating essentially a vector from this and this, and then recognizing that this is the matrix P11, 1, 2, 2, 1, 2, 2 times the vector x1, x2. So we did something like that at the end of the last class, but without it being a derivative differential equation. So to kind of review how we would do that, let's take the equation. We had the system q1 prime equals negative 0.1 q1 plus 0.075 q2 plus 1.5, and q2 prime is equal to 0.1 q1 minus 0.2 q2 plus 3. I think this was a problem that we did in a previous section, or at least set up this way. So this is a system of first order differential equations. Got our focus going crazy here. Let's try to pull that back in. There we go. And so we can rewrite this as a vector matrix equation by writing q1, q2, that's our column vector, prime, equals, then we make a matrix out of the coefficients, negative 0.1, 0.075, 0.1, negative 0.2, and then that's going to be multiplied by the vector q1, q2, plus 1.53. So in general, a system of first order linear differential equations can be written as the vector x prime, that would be our q1, q2, or x1, x2, or whatever we choose to use, equals p of t, that's our coefficient matrix, times just the vector x, plus the non-homogeneous part, g of t. So that looks just like our old first order equation, except, well, we made the p capital because it is a matrix, and these are vectors instead of just single functions. Of course, if g of t is 0, the system is homogeneous. And in that case, I guess we could write it, if we want, as x prime equals p of t x. So several of our basic rules apply. If x1, that's not a 1, x1 of t and x2 of t are solutions of x prime equals p of t x, the homogeneous equation, then c1 x1 plus c2 x2 is also a solution. So that's not how you spell solution. There you go. So then we're going to talk about the general solution. General solution, if x has n positions, coordinates, let's say coordinates. In other words, it's equal to x1, x2, all the way down to xn. Then let's see. Nope, not then yet. Has n coordinates and x1, x2, up to xn are n solutions of x prime equals p of t x and the Wronskian of each of these guys, or of all of these guys together, is not 0, then, now I can say then x1, x2, and so on up to xn form a fundamental set of solutions for x prime equals p of t x, and let's call it x equals c1 x, superscript x1 plus c2 x2, and so on till we get to cn xn is the general solution for x prime equals p of t x. So just like before, that means any solution of this differential equation can be written in this form for the choice, for some choice of constants Cn. So the Wronskian can be done as the usual determinant, but we also get the formula that the Wronskian, I should say of what? Of x1 up to xn, those vectors, is equal to c times e to the integral of p11 of t plus p22 of t, and so on until we get to pnn of t dt. All right. Let's see. But we can also find the Wronskian the usual way, if that makes more sense. So let's do this here. So the other way of saying that would be the determinant of the matrix, which was vector x1, vector x2, and so on until we have vector xn. we take that determinant. So either way works. My preference is for the determinant form. I mean, they're fine. We have a formula for each. I'm just more used to working with them in determinant form. So let's suppose, let's see. Hang on, I'm going to pause this. I just paused it for a second to double check the book and make sure I didn't have all my notes in the right spot when I started the lecture, or at least it didn't look like I did. But yeah, that's where we end today. So 7.4 is theory heavy. It's going to be a lot about the Wronskian in your homework. When we start up with 7.5, we're going to get down to actually solving these systems. That was kind of what I was misremembering. I thought we were going to solve a system today, but that's in 7.5. All right, you guys have a good one.